Okay, so good morning. We have two speakers from the US this morning, coming all the way. And George is first.
Sorry, I'll just write some preliminary things and then start talking to you.
So you have 40 minutes.
Uh-huh.
Like all the other speakers.
Yeah, whatever.
I put the alarm.
It starts when you write or when you speak.
No, sorry when I speak. Papers. Okay, thank you. It's great to be in Madrid. Thanks to the organizers and everybody. So I'm going to talk about an idea for how dark matter could be made. That in the papers we called pandemic dark matter, but Biden said the pandemic's over, so I'm going to try to not use that word too much today, and I'll just say exponentially growing dark matter. Okay. Yeah, it's these two papers with Brinkman, Depta, Nagel, Schmidt, Hoberg, and then this one. Okay. So we observe the energy density of dark matter today. Yeah, if I talk about, say, the energy density per entropy, we observe this number of 0.44 electron volts. Okay, this is about the temperature of matter radiation equality. Actually, that's what defines the temperature of radiation equality up to an order 1 factor. Okay. I can write this like so called chi dark matter, massive dark matter, number density per entropy. Okay. And then you could ask, so you could think about different ways dark matter could be produced. That'll be kind of the particle regime in this talk. And you could ask, what if whatever made dark matter gets the wrong number density? Then there are things that could increase or decrease it. So like, what if pi is produced in the wrong amount? Well, one thing that you can do if you have too much dark matter, you can deplete it by if there's some process that produces entropy. So Jan mentioned that this week with phase transitions, you can add entropy. So it's like pretty easy to deplete dark matter. If you have some entropy increase, right? Because you care about co-moving number density, so some entropy increase dilutes dark matter. Okay, so today I'm going to talk about something else. We consider the possibility of that you could increase the amount of dark matter through some number changing process where you can start with some amount and grow it into more. So it's sort of in the opposite limit. What if this is too small? It's easier, I think, to dilute because you can sort of generically add entropy. You can't really remove entropy. So how do you increase the amount of dark matter? Okay, so you can enhance dark matter by a chain reaction. That's what I'll consider here. But yeah, it'll be like some process with one dark matter in the beginning and then two dark matter come out. And then there's something up here that's not dark matter. Yeah, which generally I'll just gonna call it, say, some other state size there. Okay, so like if you have some amount, then if 1 goes to 2, if this keeps happening, you can exponentially grow the amount through a chain reaction, like a bomb or a virus. Okay, so if you have too much dark matter, you can add entropy. That's an old idea. This is a new idea. If you have too little, you can exponentially grow it through a number changing process. Yeah, so like in this case, the yield will be some initial yield times some exponential growth factor. Yeah, which in general will go, like, say, the number density of this state times this cross section per Hubble times some order 1 number. Will characterize the amount of exponential growth. Yeah.
You could also change the mass, or that doesn't.
Yeah, you could consider things to change mass, and then if you go up or down, yeah, absolutely, I agree. That would be another way to think how it's wrong. Yeah, you got to change one of these 3 things. So, yeah, I agree. Mass.
This has been looked at, no? This has been looked at.
So I haven't thought about it much.
You do if you have a web of a scalar that increase by a large amount at late time.
Yeah.
I see.
Yeah. Yeah, the changing mass would be another thing to think about it. Okay. Just you don't want to change the like electron or alpha defined structure constant very much now. Or atomic clocks will notice, but the dark matter mass, sure. Okay. This type of process in dark matter had appeared before in looking in this direction in the thermal limit, and that's called semi-annihilation. That's an old idea by Francesco D'Oramo and Jesse Taylor, circa 2010. But we're considering it in this direction in a non-equilibrium regime. So that's sort of how this is different.
What's the name of this model by those authors?
Jesse.
Yes.
Semi-annihilations.
Because I think Thomas Hamby sent me an email, and he's the first one to introduce this model.
And this, I have as you say, there's a paper before 2010.
Thomas Hamby was first on this paper.
Oh, okay. Sorry.
I also did this mistake.
Okay, so Thomas has done many things in dark matter and maybe beaten them to that.
The cannibal annihilation is only involved in dark matter. No, but it's something closer to this.
Cannibal?
Annihilation is not.
Yeah, like if you mean by like 3 to 2 processes.
But this is only involved dark matter, no, not an extra state.
Yeah, and that is also in the thermal limit. Mm-hmm. Yeah, so I'm going to consider the case where you have a very small amount where the number of chi is much less than chi equilibrium. Mm-hmm. The cannibal and semi-annihilations are you start in the equilibrium limit. Yeah, I'll be a little more precise about what I'm assuming in a moment. I just kind of want to give you a cartoon to have in your head. Okay. And yeah, so the kind of application that we focused on in this paper, but I think it's really the most interesting example of this mechanism. So if we had thought of this initially, this should have just been one paper, I think. Sorry. With sterile neutrinos, because sterile neutrinos in their simplest framework, they're not enough produced. Yeah, so suppose they're sterile neutrinos. It's kind of a very simple model for dark matter. There's that I have the sterile neutrino, a couples through Yukawa. Then you have mixing between the active neutrinos, where it says maybe and the sterile state, some mixing angle. And so if you assume that you start with very little of this and then just take the usual cosmology, then active neutrinos will oscillate into sterile neutrinos and you'll produce some amount. This is an old idea. It's called the Donaldson-Widrow mechanism. This goes back to 93. You have to do things carefully, like matter effects are important for treating these oscillations. But anyway, you'll work this out carefully, but this is constrained. The spirals will decay to actives, through diagrams like this, for example, where you made a photon. So like the interesting parameter spaces where this is say 10 kV-ish, and then you can look for a signal of an X-ray line, and if you take this mixing angle large enough to get the observed abundance, then you should have seen this X-ray line. So this Donaldson-Woodrow mechanism is excluded now from X-ray searches. So sort of the simplest version of this doesn't work. Or another way of saying it is if you just take these bounds and then say take this to be small enough, and then you calculate the abundance, then the energy density of sterols is smaller than the energy density of dark matter in the allowed parameter space. So this is a case where you back where NK is wrong in a sense, or and nu S is wrong. You predict not enough in the simplest model. So our idea is you can take this Donaldson-Woodrow amount and as an initial condition and grow it exponentially if you have a chain reaction, which can be sterile scattering actives. Then you can exponentially grow this amount and fix this problem. That's sort of the goal. Okay. Okay. There's no way I'm really going to finish this plan. So I want to kind of explain how exponential growth differs from the kind of things people normally consider for making dark matter. And that'll kind of help explain how it's different. So yeah, to do that, I will just review some things that the experts know well about. So just freeze out. And what we're talking about is a little closer to freeze in, but different. So let me kind of just explain the difference between those three. Okay. So by freeze out, it would mean something like the WIMP. Which the same story would apply to the semi-annihilations we mentioned before. Okay. So here the number density is described by the following Boltzmann equation. Okay. So freeze out is where you start with the thermal initial condition. Freeze in is sort of the opposite, where you assume you start with very little dark matter and then slowly bleed it in from interactions in the thermal bath. And those interactions can take many forms, decays or scattering. Yeah, so here psi will refer to a thermal state for me. So these are in equilibrium. So one example is like some thermal state could annihilate into dark matter. Yeah, or there could just be one of these, and sometimes it doesn't matter. But anyway, the idea is this is happening slowly, where you start with zero of this, whereas in this case you're starting with a huge amount in equilibrium and removing it through this process. Here you're starting with none of this and producing it through this process. Okay. So then there's an equation we can write. So now it'll depend on the equilibrium number density of psi times the cross section. And you can neglect the inverse process in the limit where pi is far below equilibrium. So that's a technical difference from this freeze out case where you have two terms for the two directions. Okay. So this exponential growth case will be so now it depends on the number density of chi and on the number density of this equilibrium state. Yeah, so that's a key difference here, right? In the Friesian case, the amount of dark matter you produce is independent of the amount of dark matter that's present, right? The rate of this doesn't depend on how much chi is around. The kind of new thing here, if you want to consider exponential growth, is the amount that you're making always depends on how much is present at that moment. So that's a very important difference. Okay. And if I just draw the usual yield plot, so yield is number density per entropy for me, co-moving number density, and inverse temperature. So in this case, you follow the equilibrium curve, then you freeze out. That's the famous freeze out plot, where you freeze out when the reaction becomes slower than Hubble. Okay. In this case, you start. People usually assume you start with 0, but that's actually not needed. You only need to assume you start far below equilibrium, and then it'll kind of grow by some amount, and it'll normally be dominated by order 1. Well, if I want to take this to be the maximum of m psi n chi over t. And if I do that, then this will be sort of at order 1 values of this quantity really when the production happens. Okay. Now here you need to assume some initial amount, and then when this becomes sort of on the order of Hubble, you get very rapid growth, so it'll be sort of steeper than this curve. And then you need to shut it off to not make too much, which can happen if this if these become Boltzmann depleted. So you get some curve like this. Okay. Yeah, and just to emphasize how things depend on cross sections. So famously, in this case, it goes like 1 over cross section. So larger cross section means less dark matter that you pull down the curve further. Yeah, in this case, it's the opposite. So here the amount is proportional to cross section. Okay. Whereas here, the amount depends on whatever initial amount you have that sees the growth. Yeah, times this exponential of this times order 1 number. Actually, it's not hard to do this exactly. Yeah, this equation is just the exponential growth equation. The rate of exponential growth is the rate of the reaction for Hubble. Yeah.
In the exponential case, you do need to start with some non-zero number.
Yeah, because if this were 0, then nothing happens. Yeah, that's very important.
And how do you stop the exponential process?
Yeah, I was going to say more about this more slowly in a minute, but in case I don't have time, I'll just say when either of these states becomes massive, like so when temperature drops below either mass, then you get a Boltzmann suppression in this n sigma v. So it'll be suppressed by e to the minus chi over t or e to the minus m psi over t, depending which one's heavier. Yeah, so this can be suppressed by Boltzmann, and that's how we do it.
The right-hand side of your Boltzmann equation goes to 0 somehow.
Yeah.
Okay.
Yeah, and that'll happen if the temperature drops below these masses, below whichever mass is heavier. So once one of these states is non-relativistic, this will exponentially shut off, and then you do that such that this hits the right location. Because if you grow until these, because if you don't shut this off, it'll just thermalize. You'll just enter equilibrium. So you can think of it, yeah, sort of like this would be the case where you thermalize, and then this is sort of like a failed thermalization where you hit a mass threshold before you thermalize.
So it's a half freezing process. No? If you let it go. Yeah.
I don't know what do you mean by half freezing? In both cases you're out of equilibrium. And in both cases normally you don't enter equilibrium. Yeah, if you want to produce the observed amount of dark matter, then in both cases you need to stop this before entering equilibrium.
It's an exponential freezing kind of.
Yeah, you could say that. Yeah, let me just kind of, I've already been saying it, but just to really emphasize the initial condition in these three cases, because that's a really different thing here from what we're used to. Freeze out, freeze in, and out. Okay, so for freeze out, the initial condition, well, you start with the rate much larger than Hubble. Yeah, and then NPi is in the equilibrium state. This is very nice because it's predictive, but it removes information about what happened before, which is, I guess, another way of saying it's predictive. But okay, for freeze in, people usually say they start with 0, but that's not needed. That's like a much stronger assumption than is needed. So really, you just need this NPi equilibrium. One Hubble. And then in this case, the initial condition is additive in the sense that the final abundance is whatever was the initial abundance plus the amount produced by freeze-in. Because the amount produced by freeze-in is independent of the amount that's present in the limit where you can make this assumption. People usually don't say that, but that's the assumption that's needed. Yeah, so in other words, if you can vary this height and it doesn't change the amount you move from here to here, you can shift this up and down. People don't like to say that because freeze-in is actually not predictive in this sense, but that's a situation. So here you have equilibrium, initial condition. Here you have additive, initial condition. Okay, and here you have multiplicative. Yeah, like we said, so initial abundance times this exponential. Yeah, and here you need to assume the same thing. You need to assume that initially the rate is smaller than Hubble. But whereas here the rate can always be far smaller than Hubble, and then you just add this up. For this exponential growth to happen, you want this sort of to become order 1. So you want to consider the limit where it starts smaller than Hubble, and then is some IR-dominated process that approaches Hubble, then you get exponential growth. So you want like say this, but then well, yeah, maybe not too far. So maybe that would be, what I'm saying. Okay.
You need a process that make that exponent order 1, or you just wait for the universe to cool down enough?
Yeah, so you need an IR process and then cool down enough. I mean, so this shouldn't be like generated by higher dimensional operators, which are UV dominated. Yeah.
So do you want to discuss the concrete case of the sterile neutrino, maybe, or?
Sure. Yeah, there are two. I could talk. And then if I have time, I can talk more about this kind of condition of entering and exiting equilibrium, because I can say more about that. But maybe I'll write down the sterile neutrino model and then come back to that, since you're watching the clock. Yeah, but actually that finishes this. Geraldine is suggesting basically that I jump down to here. That's fine. This example. Okay. So, consider a sterile neutrino. Yeah, for simplicity, we took the case where it just mixes with the electron neutrino, but you can consider any sterile neutrino model more generally. That's just for simplicity. Okay. And then, as I mentioned, this model alone, given observational constraints, these are necessarily metastable, and then given X-ray bounds, the region where this produces observed parameter or observed dark matter is excluded. With the exception of if you consider very large lepton asymmetries, there's a loophole there called the Fuller mechanism, where you need a lepton asymmetry that's much larger than the baryon asymmetry. So that's an interesting case where this can be saved, but up to that. If the lepton asymmetry is on the order of the size of the baryon asymmetry, then this doesn't work. Okay, so we had one thing. We had sterile neutrino self interactions. So, for example, some mediator, it could be a scalar or a vector, but obviously scalars be simple.
So sorry, can you repeat what this is the status of sterile neutrino dark matter without your mechanism?
Yeah. So the Donaldson-Woodrow mechanism just means sterile neutrino actives oscillating in, and that's excluded by X-ray bounds. The exception is if you consider a very large lepton asymmetry, then there's parameter space that works, and this is called the Fuller mechanism,
So
and it affects the medium.
The Shaposhnikov model, like.
Oh, yeah, these are.
That's C-Fuller.
Sorry?
That uses also C-Fuller mechanism, supposedly. And yeah, I mean, it's what you said, you have a really background lepton asymmetry.
Yeah.
It seems you can make it work, but it's not completely clear. There are these recent papers by what's his name? Nikolai.
Okay.
Where he tries to do the whole computation, not only of the dark matter, but also of the previous lepton asymmetry. And it's difficult to explore the whole parameter space, and there are lots of important thermal effects to take into account, so it's difficult to meditate. But it seems that it could work. The answer is not definitive, I would say, but it seems there are parts of the parameter space that could work.
Okay.
Thank you. Okay, you say this is an example where there's large lepton asymmetry.
Yeah.
Good. So I didn't lie, and that's good, even without being fully aware of the literature. Thank you.
I agree with that.
But yeah, because these oscillations depend on matter effects, very importantly, then those matter effects depend in general on whether there's a lepton asymmetry. And if you contemplate the regime, where this is much larger than this by like 1 million, then those matter effects can give dramatic, can give resonances that enhance it. But that requires, of course, if scalars set the baryon and lepton to be a similar size, then it doesn't work. So you, after scalars decouple, you need some late leptogenesis that produces a ginormous lepton asymmetry and is unrelated to the baryon asymmetry, and that's perfectly fine and allowed. But I would argue, so our model is just adding one state. So I would argue that we have the simplest way of fixing sterile neutrinos, because this Fuller idea is hiding, the complexity in that late leptogenesis that they need. So, but if you actually write down a full model, I think they'll have more degrees of freedom, or at least we just need this one state, one top one. Okay. Thank you. So, yeah, that's the model. So just so you call it off. Interaction. Okay. And then, given these two ingredients, I can insert this mixing once. That. So I can scatter a new S against new E and make two new S. And we're just mixing once. And then that leads to exponential growth if this enters equilibrium. In fact, people have considered stereo-neutrino self-interactions before us, including in literally this Lagrangian, but they missed like the cosmological importance of this reaction. So in fact, it's not even in the model. Okay. So I'll just give one example parameter point, and then you can look in our paper for a plot. But consider stereo-neutrino of 12 keV mass. Then like a mixing angle that's sort of like just below the current X-ray bounds for this mass would be like following. Yeah, they like to use this parameter, but it's like mixing angle squared is this size. Okay. For this value, the amount that's predicted by stereo-neutrino over the observed dark matter abundance is about 1/2000, given the X-ray bounds. So that's like I said, the Donaldson-Woodrow is not working given the X-ray bounds. But if you turn on this interaction, then you can take this amount and exponentially grow it into the observed amount. Yeah, and the parameters, example of parameters that would work would be 36 keV mediator, and you call up 10 to the minus 4. Turns out to work for this. Yeah, you do have dark matter self-interaction. For these parameters, those are not observable, but in general, self-interactions set a constraint or would be observable for prediction in this model. So you can test this with future X-ray experiments, and so I think that they're projected ones that actually hit this parameter point, if I remember right. But anyway, there's projected to be some improvement in X-ray, and also the self-interactions would be in general the thing here. Okay, that's an example point.
So that's one point. So you say you can test this, but I guess you have a full parameter space. Maybe.
Yeah, I have a plot. I could throw it up in the projector.
Oh, draw it, maybe?
Yeah, why not?
Yeah, so what is the lesson? So the question is, in most of the parameter space which gives dark matter, you can test it. So
given current X-ray bounds, yeah, there's some like improvement for X-ray, but there's also, and then there's a region you can test with self-interactions if we'll ever understand that, and then there's sort of a region in between that you can't. So I don't think you can test the full model. You could test some of it. Sorry.
So, but this is for the concrete scenario for the neutrinos, right? But is there a smoking gun that really tells you this is the mechanism? We will need to find, for instance, now we assume this, and we will look for this light mediator, or we look for.
Yeah. Well, sorry, of exponential growth in general, or the neutrino model? Yeah, I'd say there's no smoking gun of exponential growth. There's also no smoking gun of freeze out, and there's no smoking gun of freeze in.
Yeah. But for this model in concrete, you can look.
Yeah, in this model, there's some parameter space testable by X-ray and self-interactions, and some that's hard.
Yeah, which is cool because
it
reverse this possibility.
And similar, yeah. I mean, for these two things, I would, in any given model, there'll be some testable and some not, and there's also no smoking gun. So it's sort of the same. I'd say we're in the sort of same situation as those two. Yeah.
This is a real scale, right?
Yeah, and in the model,
you break in the number here. Well, the chiral symmetry is to
for sure, the mass of the sterile. Yeah.
So, I'm just wondering why it's not the stereo-neutrino super heavy.
Oh yeah, I mean the sterile mass is breaking up the number. Yeah, and then and it's like you think of it as spray on for a Lipton number breaking. Sorry, I was pulling up this plot to draw for you. I have time to draw the plot.
Yeah. But yes, Yalan will tell us.
Being very well behaved about the clock.
We still have 6 minutes.
6 minutes, my God. Okay. So sine squared. Sterols. Okay. Donaldson Woodrow is sort of like a line like this. Yeah, if you're PPMC, down to -11. And here we're 1, this is log. And 100. Yeah, so between, say, 1 and 100 keV, you want a mixed angle squared of 10 to the -8 to the -11 to produce the observed abundance from oscillations of active to sterols. Yeah, and then the X-ray. The X-ray line is kind of wiggly. So this is an artistic, it's kind of like a modern art museum in Madrid. Okay. Yeah, so they're X-rays. Yeah, and again, that's the signal. The new X goes to new active X-ray. Yeah, and then there's also bounce from being too warm. Kind of coming over here. This would be like, for example, Lyman alpha. Yeah, you can argue about the systematics for that, but anyway, when you get down to sort of a few kV, below 10 kV, you have to worry about this. Yes, that parameter point that I showed was over here. Yes, what do we say? It's -13. And self interactions are kind of down here. Yeah, here if we what we can do is everywhere below the Donaldson-Woodrow line, we can choose a value of these parameters to give the right amount of exponential growth to produce the observed abundance. So I think, yeah, in practice, with the plot I'm looking at, we chose a fixed mass ratio of the scalar, and then yeah. So given this choice, then there's one parameter y. So we choose y to match the observed abundance, and then as you go lower down, right, you need more exponential growth. So you need a bigger U-column, needs more self interactions. So the self interaction bound comes in the bottom of the plot. These are too much dark matter self interaction is down here. Yeah, again, just from this new self scattering, which is not suppressed by the mixing, so this happens a lot. Yeah, and then there's some projected X-ray stuff, sort of like, yeah, to hit this point, they're kind of coming in like this. Yeah, things like called Rathina. So there's sort of like, say, 1 order of magnitude improvement in mixed angle squared, 1 to 2 orders of magnitude of projected X-ray stuff here. And some people think it's interesting to consider models at the edge of here, and maybe we'll understand that better. And then this part is hard to answer. But yeah,
Is that in the Athena?
It must be. But yeah, sorry, I have to check.
So when you said there was earlier literature doing this, so what did they miss? You said, so this model had been...
Yeah, this model has been considered, but in sort of different parameter choice. Yeah, so I don't know if this process was important for the parameters they were looking at, but what people have looked at is that this generates matter effects for the sterols that can affect the oscillations. So in some of the parameter space, the Donaldson-Woodrow calculation is affected because not only the active things are in medium, but also the sterols are in medium. And you can generate, so instead of cranking up a large lepton asymmetry, you can see what's the effect of sterol medium effects on the oscillations. So people have it, in sort of a different part of the parameter space looked at that, and it's hard, but maybe. I think so. I'm not sure if it's actually working.
I think in the past it has been considered, at least in some papers I know, for the opposite purpose. So it would be interesting to interpret in the sense that it has. I know that these self-interactions of sterile neutrinos have been considered in the context of the very light steroids of that would allow you to explain the mini-boon and the anomalies of one electron volt.
Yeah.
To avoid the cosmology constraints, because cosmology does not like
to
have those around from the bounds on an effective and the sum of the neutrino masses. So they were suppressing the production via these matter effects induced by the light scalar. But then I wonder if you have something like what you described also because of the mixing. The mixing is pretty large, the one you need for mini-boon.
Yeah, that's an interesting question. I haven't looked at that literature
I
carefully.
wonder if it spoils the whole thing.
Those EV scale sterols that people invoke for those anomalies, of course, cannot be all dark matter because it's too warm and the remain gunbound and so on. But indeed, the cosmology of them is interesting, and then this process could play a role in those papers. So we haven't looked at that yet. This exponential growth process happens generically, and as far as we're aware, hadn't been considered before. So that's something to consider when you study the cosmology.
Right. So I think we are done and we ask questions now. Thanks a lot.